So it's really exciting to be finally standing here and talking to Saturday Morning Physics. It's something that I found out about as soon as I got to Michigan. And it was something I thought was really exciting. So I emailed them straight away and I said, I would really like to give a talk. Please sign me up. And this was, of course, 3 years ago, right? And finally, I got my chance. But all things happen for a good reason. So 3 years ago, I would have talked to you about something completely different. But in the 3 years I've been here, there's been a very interesting change in the way physicists think about the early universe. And it's been fueled by discoveries that have been made in the last few years. And therefore, that's going to be the topic of my talk. And I've put up, as you can see, a very unassuming, modest title, Higgs and the Beginning of the Universe. Right? What could that possibly be? I should say straight away that there are no equations in the talk. So you really have no excuse to go down into your cell phones or take a nap. This is going to be a fun talk, right? It's going to be a very interesting story, a story that's actually true, that's actually what might be happening in our universe. And this has all happened so rapidly over the past few years, and I think it's going to be a really exciting talk, right? And in the beginning, it all started with the Big Bang. I have to ask, how many people recognize this picture? Yes. So my first joke did not fall flat on its face. So it all starts with the Big Bang, and as we all know, if we follow our TV shows religiously, and I keep forgetting that this doesn't work, we know that our whole universe was in a hot, dense state, and then 14 billion years ago, expansion started, right? But before the Earth began to cool and all those things happened, wait, there was something that was very exciting that might have happened as the universe started and was cooling. And this talk is going to be the story of what happened right at the end of that expansion. So this talk is going to be driven by two main observations. The first one, 4th of July 2012, scientists at CERN, at the Large Hadron Collider, decided that they had got enough data to be able to announce that they had discovered the long sought after Higgs boson. So that was probably the biggest piece of discovery in my lifetime. And it happened a few years ago and was very exciting. Many sleepless nights thinking about what it meant and writing papers. And so this is going to be the first piece of information that will start us on this talk. The second discovery that was not made not too long ago, gravitational waves, right? So you all heard about this just last week or a couple of weeks ago. Saturday Morning Physics was about the discovery of gravitational waves that happened earlier this year. Unfortunately, this is not going to be part of my talk. So when I say gravitational waves, I don't actually mean this one. I meant the gravitational waves that were supposedly discovered even earlier. So if you remember 2014, there were all these rumors or all these announcements and fanfare that they had, in fact, discovered gravitational waves of a different kind. And so this was the more interesting kind, at least to me and a lot of other people. And it was interesting because supposedly this was a detection from the afterglow of the Big Bang, right? So the claim was, so I've underlined it, it is the proof of cosmic inflation that physicists had been eagerly awaiting. It opens a window into the unification of the fundamental forces of nature and into quantum gravity. So I could not have written bigger words if I tried. So this was supposed to be a huge discovery, and it would have meant a very big thing for people working on phenomenology and cosmology and particle physics. Unfortunately, this was not to be, too good to be true. So this announcement was later retracted because they found out that they hadn't properly subtracted some dust contribution. And when they did, the signal went away. But maybe we'll discover it sometime in the future. But for the few months that we thought this signal was real, the topic that I'm going to tell you about really took momentum. And a lot of people started thinking about this. And that's what the talk is going to be about. So I've been talking for about 5 minutes now. And this is about when people start falling asleep, right? And so someone once told me that the best way to prevent people from falling asleep is to give a pop quiz. So here's a pop quiz. I'm going to throw some words on the board, and if you are familiar with that word, if you know what that means, please, let's get a show of hands. So Higgs boson. Everybody, good. Inflation, and I don't mean the economic, monetary kind, right? The important one, cosmic inflation. Good. Next up is quantum mechanics. And just in case you start thinking that you know everything, Hawking mass instanton. All right, how about anti-de Sitter space? Okay, here's might be an easy one, black holes. Finally, the multiverse. All right, so I think most of you passed, and hopefully most of you woke up from your slumber. But what I've really listed here is basically the outline of my talk. So we're going to be talking about all of these things. So we'll start talking about inflation and the Higgs boson, and these two were, of course, the discoveries that were made, and we're going to think about what these have to do with the rest of these. So there will be quantum mechanics, we will get a Hawking-Moss instanton, we will go into anti-de Sitter spaces, there will be black holes, it's a promise, and there might even be talk about a multiverse, depending on how fast I finish or how slow I finish. So let's start with inflation. Right, so this is a picture of what might have happened in the early universe. And so this is today. You see your stars and galaxies. And as you go further and further back in time, there's the Big Bang. And right at the beginning, there was inflation. There were quantum fluctuations, and there was inflation. Now, inflation is just a theory, right? So which means we have not actually seen any direct evidence that it actually happened in our early universe. But it's something that most of us believe did happen, and we have very strong reasons for believing that it happened. So first of all, what is inflation? So inflation is this early period of extremely rapid expansion when space-time expanded very rapidly. And so when I say very rapidly, I mean exponentially, so even faster than the speed of light. So that sounds odd because we've been told that nothing can travel faster than the speed of light in space, right? But if you read the fine print, as always, there's a caveat. And the caveat is that space itself can travel faster than the speed of light. And nothing prevents that in our equations. And space does, in fact, expand faster than the speed of light at some very early time in the universe. How fast? It grows by a factor of about 10 to the 70 in 10 to the minus 33 seconds. So I'm talking about super rapid expansion, right? Everything gets stretched out super fast. So it starts with something like that. So the small dots grow bigger and bigger very rapidly. And our universe grows from something very, very small to something a lot larger in a very short amount of time. And the physical parameter that controls how this happens is called the Hubble parameter. So the expansion rate is e to the 3h times time. So it grows exponentially with how big this Hubble parameter is. And so this is a parameter that you should know by heart or remember by heart because this is going to show up again and again in the rest of this talk. Right, so inflation is expansion of space-time very rapidly. Why do we think there is inflation? We think there's inflation because we do not know a lot of things about the universe. To list a few, we don't know why the universe is so smooth on very large scales, which means if you look out into the universe, I look at one corner of the sky, I look at another corner of the sky, they are as far apart as they can possibly be, right? And if I stretch back my physics, in fact, they were never close enough that they could have talked to each other. So I would have expected them to evolve randomly. But it turns out that all over the sky, the temperature is very uniform. And that means the universe overall is very homogeneous. And we don't understand why that is, because we expect them to be very different. So that's the first thing. The second thing is that the universe appears to be very flat. By flat, I mean that space-time can have some curvature. The universe turns out not to have a lot of curvature. So essentially, flat universe. And we don't know why the universe evolved in such a way as to become so flat. Next on the list, there are relics that we expect to see in the universe that are missing. By relics, I mean things that get produced early in the universe. To give a very concrete example, physicists talk about grand unified theories of nature. Those grand unified theories of nature predict that there should be monopoles in nature, magnetic monopoles. So these are things that no one has ever seen, right? You've tried to break your magnet. It again turns into a north pole and a south pole. It's not a monopole. We've never seen a monopole. But physics predicts that there should have been huge, massive monopoles early in the universe. They should have stuck around to today, and we should have been able to see them. We don't see any monopoles. So why are these things missing? We don't understand that. And finally, we don't understand why there are inhomogeneities at a small scale. So I told you that the large-scale universe is very homogeneous, but at small scales, there are small inhomogeneities. And that's what grew into galaxies and clusters and all those things. If the universe were absolutely uniform, matter would not have known where to start condensing and forming structures, right? So we know for sure that there are small-scale inhomogeneities in the early universe. And so this list of things that we do not understand goes away if you assume that inflation happened in the early universe. And there's actually a very elegant explanation for why all of these go away. It's so elegant that I can put it in a picture. Right? So here is what the universe early on might have looked like. M stands for monopoles, not Michigan. So there are monopoles everywhere in the early universe. Space, as you can see, was very curved. And you can imagine that all of these patches are slightly different, so it was not a homogeneous universe. Right? But as I take it and inflate it very rapidly, a few things happen. So as I go from there to there to there to there, the monopoles start disappearing because they just get stretched out so far away from each other that today we don't see any of them. So that takes care of the missing relics. As you can see, this curved space becomes more and more flat as things get stretched out. Right? So it makes sense. As I take something that's curved, stretch it out to a very large scale, it looks very flat. And it's true, for example, of the surface of the Earth. Right? So the Earth is huge and it's round, but we don't see that it's round because it's so large. And to all our purposes, it looks flat. And so inflation might have done something like that to space. Inhomogeneities also make sense because early in the universe, there were quantum fluctuations. Right? So quantum mechanics tells us that there are quantum fluctuations everywhere. And early on in the universe, if I imagine a small quantum fluctuation happening, usually it just vanishes. Right? But if space is inflating, that small quantum fluctuation gets stretched out also. And when inflation ends, that can start the seed for structure formation. So this small overdensity might be where mass starts collecting, and that eventually forms our structures that we see today. The one that I've left out is smoothness, and you can sort of imagine why stretching things out might make it smooth, right? So if there's a lot of different patches, then when things get stretched out, I only see one patch, and so that appears more smooth than it would have normally looked like. But I've saved it because I need a different slide to show it, and I want to show it because this is actually something that's very relevant for the rest of my talk. So what do I mean by inflation explains why the universe is homogeneous? So if you look at the big circle to the far right, this is what the universe looks like today. And so let's focus on a few points, right? So there's where we are sitting. This is where the Milky Way is. At the center, there is a point A in space, point B in space, and those are the farthest points in space that we can see. So as of today, this is when light is just arriving to us from those faraway points. What that means, of course, is that as I go backward in time, the region from where light could have reached me gets smaller and smaller. Right? So if light was just getting to us today from these points A and B, that means earlier on, they would have been too far away for light to get to us. Light can only get to us from this dotted circle in the middle sphere. And so the fact that point A and B have exactly the same temperature is very puzzling, because if I go back to what it would have looked like earlier, there's no way they could have talked to each other, right? So no information would have been able to go from A to B because nothing can travel faster than the speed of light. And so you would have imagined that A and B never talk to each other, and so they should never know about what the other guy's temperature is. This picture changes if I put in inflation, because if I stretch this back even further to before inflation happened, which is the small circle to the far left, then remember that inflation involves space traveling faster than the speed of light. Right? So if I run this movie backwards, space crunches faster than the speed of light. And so these two objects, A and B, that would have been so far away that they could have never talked to each other, were in fact inside this circle where light can communicate with each other. So that means that before inflation, or at some point during inflation, they were in fact communicating with each other, so their temperatures were able to thermalize. And that's why much, much later today, we can see that their temperatures are about the same, and that makes sense if inflation happened in the early universe. So this is a crucial aspect of inflation, and this will be crucial for the rest of my talk. So distances grew faster than the speed of light, so please remember that. And points that appear too far today were actually in causal contact before inflation. So those are the things you should remember if you forgot everything else from the last 5 minutes. So what causes inflation, right? So I told you that inflation happens. Something should have caused it. And the way we understand it is that inflation needs a tremendous energy density stored in the early universe, and it has to be stored in a special way. So you can't have a lot of particles moving around. That energy is not good enough. The way it needs to be stored is that it needs to be stored in the potential energy of a scalar field, because we need a source of energy that does not fluctuate and does not change over time much. So the way we imagine that this happens is that there is a field called the inflaton, right? Inflaton gives inflation, makes perfect sense. It has a huge potential energy during the period of inflation. So early on, this field was sitting on some potential that was very high in energy. And as time went forward, it started rolling down this hill. And when it finished rolling down the hill and started oscillating, that's when inflation ended. So that is our picture of how inflation happens. And the energy scale of inflation is set by the potential energy of this inflaton field. And this h is the Hubble parameter I told you about earlier, which sets how fast space expands. So the Hubble parameter tells you how fast space is expanding, and it tells you what the energy scale of inflation was. So this is our picture, a theorist's picture, or a phenomenologist's even picture of inflation. And so just to remind you of the key concepts, because if you miss these points, you'll miss the rest of the talk, right? So the key concepts in inflation are that, one, it requires this tremendous energy density in the early universe. And if there's no energy density, there's no inflation. So you need a lot of energy density, point one. Right? Point two is that during inflation, distances grow faster than the speed of light. Faster than the speed of light is crucial. And finally, I should also add that we actually have no measurement of what this scale of inflation is. So this is an unknown about the early universe that we would like to know someday. So that's my mini talk about inflation. Let's move on to the second part of my introduction, which is the Higgs. Right? And so here is the I would like to call it the periodic table of subatomic particles. And I'm sure that this was designed by someone who was a chemistry student and hated having to memorize the chemical periodic table, right? So this one's much more simple and elegant and has fewer things to memorize. But it has our quarks and leptons that form all of matter. It has these gauge bosons that carry the different forces. So photon carries the electromagnetic force, the weak gauge bosons carry the weak force, and the gluon carries the strong force. And so in this box, we have everything that we've seen in this universe, right? So everything from this table to my pointer to mountains to stars to galaxies, everything is explained by this collection of boxes. And for the past 50 or 60 years, or well, that might be going too far, but for the past few decades, we have known all of these things, and there's been something that's been very puzzling in this picture because it needed a completion. And that completion was that there needed to be a Higgs boson to complete this picture. And because I have copied this slide from a few years ago, it says the Higgs boson is yet to be confirmed. And of course, that's not true anymore, right? The Higgs boson has been confirmed as of July 4th, 2012. We know that it weighs a healthy mass of 125 GeV. A GeV is a unit of energy that will come up again and again in this talk. So for reference, a proton mass is about 1 GeV. The Higgs scale is about 100 GeV. And this is the scale also of electromagnetic forces, or electroweak forces, I should say. And so the Higgs boson was finally discovered, and we were all happy. And the reason we were all happy was because we need the Higgs to complete this picture, and we need the Higgs to complete this picture because without the Higgs, everything is massless. Right? So this is the picture that physicists will tell you. And I'm sure you've heard about this several times, but just to dedicate one slide to it, the Higgs, what it does is that it has a non-zero value in vacuum. Right? So that's the crucial thing about the Higgs. In vacuum, it's not vanishing. It does something strange. It has a non-zero value, and it's everywhere in space, because wherever there's vacuum, there's a Higgs field, and it has some non-zero number. And what happens is that all the particles we know travel through this Higgs field When they travel to this Higgs field, they interact with the Higgs field, and the strength of their interaction gives them masses. Right? So anything that interacts strongly will get a bigger mass. Anything that interacts weakly will get a small mass. And so we're living in this ocean, if you like, of the Higgs field. And as things wade across, they get dragged back. Right? So something that's big, like this guy, say the top quark, has a massive drag force, and therefore it feels very heavy. Right? And on the other hand, something like the small guys, say the electron, does not feel the drag too strongly, and therefore electrons are light. And so we've had this picture that the Higgs can give masses to these particles for a long time, and finally it was discovered. But what we needed to do was find out what the mass of the Higgs was and how it got a vacuum expectation value. And the way it gets a non-zero value, right, is that things have potential energy. And so this is basic picture. So the Higgs field lives in a potential that is shaped like this. It would like to live at 0. And if it lived at 0, nothing interesting would happen, right? So everything would be massless. But the Higgs potential just happens to be shaped this way. It's called the Mexican hat potential everywhere. I don't know what they call it in Mexico. Maybe just the hat potential, right? But anyway, so we've known that we needed something like this for the Higgs mechanism to work. So we know for sure that the Higgs potential needs to have a minimum like this. And as we all know from studying physics in kindergarten, right, things always tend to move to the lowest point. That is the most energetically favored configuration. So if the Higgs field sees that living down there is a lower point, then it will like to live down there, and that's where the Higgs lives. So if I take out all the energy from the Higgs field, it just sits there at the bottom of this potential, but then at the bottom of this potential, its value is not 0, right? So its value is about 174 GeV, and that is the vacuum expectation value of the Higgs field, and that's where the Higgs field sits everywhere in the universe, even when there's no energy. And so we've known this picture for a long time, but we then discovered the Higgs, and what it allowed us to do is that it allowed us to translate information about the Higgs mass into information about the shape of the potential. So for the first time, we could actually extend this potential further and see how it evolves as we grow to higher Higgs values. And when we did that, something very strange appeared. The Higgs potential, turns out, actually flips over. So this is the picture I had shown you earlier. From our measurements, we can extrapolate what that shape would look like. And as it turns out, it keeps going up and up and up and up, as we would expect. But at some point, at very high energies, so I've normalized things so that the x-axis, which lists the Higgs mass, is normalized to this scale that is 10 to the 10 GeV. So at 10 to the 10 GeV, the Higgs potential actually flips over. Right? And so we always thought that the Higgs lived at its true minimum, and the true minimum was somewhere down there, but that was actually not true. The true minimum is actually somewhere down there, and that is not our universe. So for a Higgs, or for a universe that looks like ours, the Higgs has to stay here. And you can definitely tell that this is a Higgs because it has a face that looks like a Higgs, right? So the potential might be shaped like this, but the Higgs absolutely has to live here. It cannot live down there because that is not our universe. And so the game now is that we would like, even though the Higgs potential is shaped like this, for the Higgs to always live in this vacuum that gives us our universe. This is the electroweak vacuum, right? And that is the vacuum we know and love, and that is where we would like to live. So immediately there's a problem, because if you just randomly place the Higgs anywhere on this possible range of values, the probability that the Higgs lands inside this potential wall is 1 in 10 to the 9. Right? So if the Higgs value were randomly selected early on at the beginning of the universe, there is this tiny, tiny chance that we would end up in a vacuum that looked like ours. So this is a little disturbing maybe, but then you say, well, there must be things going on in the universe that we don't know about in the early stages, so maybe something picks this value and puts the Higgs there. And then we shouldn't really worry about all this bad area that the Higgs could have been sitting in. And so you could go with this philosophy, but that does not solve all your problems, right? Because even though you're sitting in a place that looks very safe because you're saved from this true vacuum by this potential barrier, once you put in quantum mechanics, there is this phenomenon called quantum tunneling, right? So quantum tunneling tells us that an object can actually penetrate a barrier that you would think is classically not allowed. There's a non-zero chance for this to happen. Right? So you could try this. You could try walking through that wall, for example. And people have calculated what the probability of going through that wall is. Turns out that if you try it every second, you will get through at some point after the end of the universe. So if you have plenty of time, you're free to try it. I'm not taking any responsibilities for bloody noses. But this is an actual thing that happens, and people have seen this on a lab scale with smaller objects, right? So elementary particles exhibit this phenomenon. And so really, it is true that even though there is a classical barrier that you would have otherwise not gone through, quantum mechanics tells you that you can actually go through it straight through. And this was news to me because I was thinking back to all these times that my mom would scream at me for my socks ending up on my bed instead of outside the door. So if I had known this, so Mom, if you're watching, there is a scientific reason for why that happened, right? But I'm digressing. So to get back to our setup, this is very clearly applicable to the picture I was showing you before, right? So the Higgs sits in this electroweak vacuum, and we thought that there was this classical barrier that it couldn't have gone through, but that's not true. Quantum tunneling tells us that it can go straight through this barrier, and there is a probability for that happening. And once it goes through, it appears on this other side of the wall, and it's downhill, literally downhill from there, right? And so I've switched the colors to show you that something dangerous is happening, and therefore the Higgs has gone red. So remember that white is good vacuum, red is this going into this true vacuum, and that'll be a color code I follow for the rest of my talk. And so this is a little alarming, but not completely catastrophic yet, but a little alarming because we don't know what are the chances of this happening. So you sit down and try to calculate what are the chances of this tunneling actually taking place. It turns out that this rate is really sensitive to what the shape of this potential wall is. The shape of this wall, on the other hand, is sensitive to things like the exact mass of the Higgs, the exact mass of the top quark, which is the particle that the Higgs interacts most strongly with, the strength of the strong coupling, and all those things. So let me show you a plot where all these things are probed. So this is a pretty hefty plot, so let me tell you what the axes are. So on the x-axis, you have the Higgs mass. So the Higgs mass being anywhere from 0 to 220 GeV. And the top mass is on the y-axis, and the top mass, say it was anything from 0 to 220 GeV. And so you look at what these different mass parameters imply for what the tunneling rate through that potential well is. So there are three distinct color codes, green, yellow, and red. And as always, red signifies danger, green signifies everything is good. Ignore this part where it says non-perturbativity for now. But let me tell you about these three things. Right? So instability means that flip over actually happens and the true vacuum exists. And the time scale for tunneling through to that true vacuum is less than the age of the universe. In other words, we could not have lived in a universe like that, right? Because even if the universe started with the Higgs field sitting smack at the center at the electroweak vacuum, it would tunnel through very quickly to this true vacuum and would have ended up in a universe that was vastly different. So the electroweak vacuum is unstable in this part of the parameter space. That is red. So that is bad. Let me switch to green. Green is where things are good, right? And things are good because either the shape of the potential is such that it never flips over, actually. So the electroweak vacuum is, in fact, the true vacuum, and we keep on living there forever. Or even if it turns over, it's not lower than the true vacuum, the electroweak vacuum. So in other words, if you're living in a combination that gives you a green point, things are good. There is an interesting region smack in between the green and the red, right? And there it says that the vacuum is metastable. So metastable means that there is a true vacuum that is not our vacuum, but the time scale for tunneling from our vacuum to that vacuum is actually much longer than the age of our universe. So our universe could be sitting there, and it would look just like the universe that we see now, except there is a non-zero chance that we will actually tunnel into that true vacuum at some point in the future. And so we know what the mass of these guys are now. So the mass of the Higgs boson, as I just told you, is about 126 GeV. The mass of the top quark is about 173 GeV. And so we are living smack in the middle of metastability and instability, more in metastability. So let me zoom into that square, and things will get a little clearer. So these circles represent the 1, 2, and 3 sigma values for the Higgs and the top masses. So we know the top mass within this uncertainty, we know the Higgs mass within this uncertainty, but within those uncertainties, we most likely live in a vacuum that is metastable. Right? So in other words, that flip over that I showed you earlier actually happens. There is actually a true vacuum, and the lifetime for us to go into that true vacuum is longer than the age of the universe. And that's what happens in all of these yellow patches. In the green, it's slightly stable, but then we most likely are not living in a green region. So we are faced with this possibility that we're living in a metastable vacuum. And we are faced with this scenario that we might be okay with this, right? So there's a vacuum out there, we might go into it, but there's a very tiny chance that we would have gone into it, so our universe can live on forever, essentially, not forever, but for a long, long time. And so we should be okay with this, and so none of us are dying yet. However, there is a different way for the Higgs to end up over there, right? So I could place it there, I could tunnel through, but I could also excite it thermally. Right? So this is something that happens, for example, when you boil water and you put in something light, you see that it jiggles a lot, right? Because it gets all these thermal fluctuations, because the temperature is so high that the universe is boiling, essentially, that anything that's in there gets this thermal kick around, and that kick around might actually kick it to the top of this potential, and then nothing prevents it from rolling down. So this is something that might have happened if the temperature of the universe was high enough. And let's think back about when the temperature or the energy density in the universe was super high. And that was, of course, the period of inflation. Right? So during inflation, where you had this tremendous energy density in the universe so that the universe could expand, what it could have also done is give this Higgs field thermal excitations to take it to the top of the barrier and over to the true vacuum. And so this is something that gives you fluctuations to the Higgs field of the size that goes as the Hubble scale over 2 pi. But this is something that could have happened during inflation. So if you know a little bit about inflation, you would at this point say, don't be silly, right? So don't be silly. The analogy breaks down because there are actually no particles in the universe during inflation. So there's actually no radiation, no thermal excitations, no fluctuations that can come from something like boiling water. So this analogy is moot, and you should not be worried about it. Of course, if you know a little bit more, you say that that is not exactly what is happening, but what's happening is something very similar, and it's something very similar that we have known and understood from elsewhere. So the analogy is to a black hole. Right? So we know that black holes do not emit anything, because anything that goes into the black hole, light included, has no chance of escaping out again. And yet we talk about black holes radiating, right? So black holes apparently give out radiation, and they have a temperature, even though there are no particles coming out of the black hole. So how does that happen? So the way that happens, and a lot of you maybe know about this, is that the special thing about black holes is that there is an event horizon. Right? So an event horizon is where you're essentially drawing a line between where particles could fall in and never come back out again. And so when an event horizon exists, as it does for a black hole, people have understood that there are quantum fluctuations in space that are happening all the time. Right? So we say that energy is conserved, but energy is actually not conserved on very small timescales. So on very small timescales, you could produce a particle and antiparticle out of nothing, just out of vacuum. There's a fluctuation, you get 2 particles, but then a very short time later, they merge and annihilate each other. And so energy is conserved over a very short time scale, but not at shorter time scales. And if that happens close to the horizon of a black hole, something non-trivial happens, right? Which is that you produce a particle and an antiparticle, but if they're produced right on the horizon, one of the particles has fallen into the black hole, so the other particle does not have anything to interact with, and it just becomes a free particle, and it goes off, right? And so when we look at it, it seems like the black hole is radiating energy. It's radiating particles. So what's really happening is that when you combine quantum fluctuations that are happening everywhere in space with an event horizon, you get this effect that there seems to be radiation. Well, I told you that in inflation, space is traveling faster than the speed of light. And when that happens, that gives rise to an event horizon. So let's look back at this picture of inflation. Right? So if I'm sitting here in an inflating space-time, then there is a limit in space beyond which things are traveling away from me at faster than the speed of light. Right? So that by definition means that anything outside that circle can never give any information to me. And so what can happen is that you can again get these pair production of virtual particles right on the horizon. One of them goes outside your sphere of ever being able to see it. The other one comes towards you. And then you essentially have radiation out of the event horizon, even though there are no particles in the universe. And so the picture is exactly the same as a black hole. And this is a well-studied effect, and it's called the Gibbons-Hawking temperature, or the de Sitter temperature, because inflating space-time is called de Sitter temperature. So inflating space-times do have this property that there is radiation, even though there are no particles. And so there are actually quantum fluctuations. So these are not thermal fluctuations, these are quantum fluctuations. What these quantum fluctuations can do is excite the Higgs field from all the way from its safe spot at the electroweak vacuum all the way up to the top of the barrier and over towards the dangerous minimum. And as I told you earlier, the fluctuations are of the size, the Hubble scale. And so if the Hubble scale is much larger than the scale of this potential well, then you can imagine that you will most likely get knocked out of this true vacuum. And in fact, if H, which is the Hubble scale, is any bigger than this instability scale, you essentially get a 100% probability that you will go from this white Higgs to a red Higgs. Right, so this sounds dangerous. But let's hold back on judgment and try to find out what actually happens when the Higgs field rolls down to the true vacuum. What happens to that region of space-time? And I apologize for the quality of these pictures. As you can imagine, these were made hastily and are not part of a publication. So this is something I made a few months ago to send to my collaborators. So things are not very clear, but let me explain to you what the various things are. The top plot shows you how the various energy components in the universe evolve as the Higgs field rolls down. So there is, in green, there is this absolutely flat line. That is the energy density in the inflaton field. Right? So that is constant, and that is what keeps the universe inflating. But then as the Higgs rolls down its minimum, it is losing potential energy. Right? And that is this yellow curve. So it's losing potential energy. But then whatever it loses in potential energy, it gains in kinetic energy. The two are actually not equal and opposite. So something weird happens in an inflating universe, that the potential energy you gain is actually less than the kinetic energy you gain is less than the potential energy you use. So the net effect is that you start losing total energy. And the total energy is in blue. So what happens is that as the Higgs field rolls down, the total energy density in the universe starts decreasing. It starts decreasing, it eventually goes to zero because the negative potential energy of the Higgs becomes the dominant force in the universe. And then it goes back again, goes back up again. The more interesting thing to look at is how the Hubble parameter changes. So remember that I told you that the Hubble parameter was the thing that tells you how fast space is inflating, right? So inflation goes as e to the 3ht. That's what the Hubble parameter tells you. And so what happens when the Higgs field rolls down its slope is that the Hubble parameter starts decreasing. It goes to zero, and it goes negative. So this is really interesting, right? So at some point, the Hubble parameter vanishes, and then it becomes negative. So e to the 3ht, from becoming a very rapidly growing number, becomes a very rapidly decreasing number, because h is negative. And so that's the difference between the two sides of the potential. So if the Higgs is sitting in the electroweak vacuum, Hubble parameter is positive, space is inflating because it's de Sitter space, it has positive energy density, and so things are stretching away from each other. As soon as the Higgs starts rolling down its potential towards the true vacuum, the sign of the Hubble field changes, and that means that space is now crunching instead of expanding. So there's no inflation. On the other hand, everything collapses onto itself. Right? And so everything does this, and this is called anti-de Sitter space. The anti meaning that it's the opposite of de Sitter, as in it's crunching instead of expanding. And so now we can definitely say that this picture is catastrophic. Right? You do not want to do this. So if you go home now, tell your kids, don't do this ever. Right? Don't put the Higgs in the true vacuum. Because in the true vacuum, space just collapses onto itself and everything vanishes. And you definitely cannot live in a universe like that. So this is a very intuitive picture, and this is actually more rigorously known as the Hawking-Moss instanton, where you try to solve this system and you follow the equations of physics, and it tells you that one of the solutions is, in fact, that the Hubble field, or the Higgs field, is sitting at the top of its barrier everywhere in space. So this solution is called the Hawking-Moss instanton, and that tells you that one of the energetically stable configurations for the Higgs field is for the Higgs just to jump to the top of the barrier everywhere in space. All right, so everywhere is highlighted or in capital letters, because everywhere has a caveat, and the caveat is that everywhere is not everywhere. So what does that mean? Right? So going back to inflation, I told you that during inflation, things are traveling away faster than the speed of light, and there is an event horizon beyond which information cannot pass. So that means that if my Higgs transitioned to the true vacuum at some point in space, this would only be confined to within the event horizon. Right? So everywhere outside is moving away so rapidly that this transition, this information never gets to this point. So in all of these parts of space-time, the Higgs is actually happy and in an electric vacuum and does not care at all that in some other part of space, the Higgs has fallen into the true vacuum. And so you can see that the picture is a little complicated now. So let's think about this more carefully. So this is the most complicated slide I have, so pay extra attention. So let's talk about things in terms of E-folds. Right, so an E-fold is when space grows by an exponential factor, so by a factor of E, which is about 3. So to go back, actually, this part of space-time that's causally in contact, I will call a Hubble patch. So a Hubble patch is a size of space that is in contact with itself. All right, so with that, let's think about an E-fold. So every E-fold, right, this direction grows by a factor of 3, this direction grows by a factor of 3, this direction grows by a factor of 3. So if I start with a Hubble patch, I end up with 27 Hubble patches, because that's how space grows. Right, so every E-fold, my Hubble patches are multiplying by a factor of 27. So I give you a list of things that inflation needed to solve, and it turns out that for inflation to solve them, there need to be at least 60 E-folds of inflation happening. Right? So if I start off with a single Hubble patch in the beginning, that means that I end up with at least e to the 180 distinct Hubble patches at the end of inflation. And all these patches don't talk to each other because they are so far away from each other, or receding so far away from each other, that even at the speed of light, they could not talk to each other. So the Higgs, in a sense, does this random walk over all these different patches. And what we really want is for when all the dust settles and inflation is ended, we want the Higgs to be sitting in the electric vacuum and not in the true vacuum at the end of this evolution in all these different patches. Right? So let's follow one patch and see what the probability is for the Higgs to be safe. And so here's different ways of calculating it. And so you should be looking at this curve that has all the red crosses. And that tells you that as soon as, so the x-axis is the Hubble scale as a function of the cutoff energy. So as soon as h is bigger than 1, right? So as soon as the fluctuations are bigger than the barrier, the probability for living in the electric vacuum starts going down. And it goes down pretty rapidly as you go down. And this is for a single Hubble patch. The picture is actually more complicated because at the end of inflation, there are many, many, many Hubble patches, right? So I could not copy paste this e to the 180 times, but you get the idea, right? So there's many, many different Hubble patches. They're all doing their own things. In some of them, the Higgs is in the nice vacuum, the good vacuum, the electroweak vacuum, but in the others, it's in this bad vacuum. And so the question really is what happens when inflation ends and all these things can again talk to each other. So an optimist would say that all these bad vacua are anti-de Sitter space, and remember that anti-de Sitter space is crunching space. So an optimist would say, oh, all of these bad vacua will just crunch and disappear, and all that is left is the white Higgs pictures, and so everything is fine. A pessimist, on the other hand, would say that, no, you're getting it wrong. The bad vacua are the vacua that are more stable. Right? So that is the true minimum. So that should be more energetically favorable. So what should happen is that all of these red patches should grow and eat up all these white patches. And so this will eat up everything, and to put it mildly, we're all going to die. Of course, there's the third guy, the realist, who also happens to be a physicist. And he says, this is fascinating. Let's do the physics and see what the physics says. And so let's all be realists for now and see what the physics says. So let's look at one bad vacuum, right? So you nucleate this bad vacuum, and it evolves to a shape of a bubble. And this bubble is surrounded by the good vacuum. And so the question is, how does this bubble evolve in time? So there are two forces in play here. One is that a bubble wall has tension, right? And so it wants to squeeze itself in as much as possible. So this favors the bubbles shrinking and disappearing. But then there is a different effect where, remember that the inside vacuum is more stable than the outside vacuum. So there is a pressure for the bubble to actually expand so that more of the universe can be in the true vacuum, which is energetically more stable. And so the question really is, who wins, right? So in this fight between good and bad, as you can imagine, the bad always wins. And the bad always wins, especially when you're in the middle of a talk and not at the end of the talk. So the bad win. So apparently, in most of the parameter space, the bad happens to win. And so these bubbles actually expand. What that means is that if I start off with these bubbles of true vacuum, even though the space inside them is crunching and disappearing, the bubbles itself will grow and merge into each other and eat everything up. And that's just what seems to happen in all of the universe. And so what it feels like is something that I've thought about, and the best I could come up with to explain that sensation is probably something like this. So you're sitting in the good vacuum, you're playing with your toys, everything is fine, and you look around, nothing suspicious, and then bam, the true vacuum gets to you, right? So an ADS bubble gets to you, it eats you up, and the universe is over. This is, of course, a cartoonist rendition and not the actual physics. All right, so looks like we're doomed, but then as physicists, we never give up, right? So you think about what else could you do? How else could you save yourself? Are there any other ways? And it turns out there's one other way to do it, and that one other way involves a black hole. So black hole 101, one thing we all know about black holes is that they are formed when you crunch in a lot of energy and mass into a very tiny part of space, right? So if I could squeeze a lot of energy into a small region of space, I form a black hole. And the one thing I know about black hole is that once you trap something inside a black hole, it never gets out. So again, don't tell my mom about this. But this is one way that you could imagine solving this issue, right? So what if the initial fluctuation had so much energy and it happened in such a small region of space that it would form a black hole? Because then the bubbles can expand, but they will only expand inside the black hole, and then it'll never get to me. And in this way, I can save the universe. So this is fascinating, right? So this is interstellar sequel material. But then you do the calculation, and so what it actually means for a bubble to expand inside a black hole, because it sounds counterintuitive. So you have a boundary beyond which something cannot expand, yet it is always expanding as the equations tell us. So what it actually looks like is as follows. So you have something trapped inside a black hole. It starts expanding, but when it expands, it actually pinches itself off from the rest of space-time. So what's happening is that you're basically creating a baby universe that lives inside a black hole. And it can keep expanding, but it keeps expanding. So you can see that this bubble can get bigger and bigger, right? But it'll never get out of this black hole. So this is something that might happen if numbers line up correctly. So you might have expanding bubbles of bad vacuum, but they are always in a black hole, and they never get to us. Unfortunately, again, it happens only for very extreme values, so most likely this is not something that happens. So you have to think about other ways to save our universe. So let's start making a list, since we're saying a lot of things, right? So how could I save my universe? There are many ways to do it. So I said, if the Hubble scale, for example, is smaller than the instability scale of the Higgs, the universe is safe. If that doesn't happen, then maybe the bubbles are formed in such a way that they prefer to shrink rather than expand. which means the tension wins over the pressure. And then we found out that that was also most likely not the case. And then we thought that maybe we could put them in black holes and hide them away in our closets, and nobody would ever have to know that they existed. And that also did not work out. And this is where a particle physicist comes in and says, I have many other ways to save your universe. Let me list a few. So the idea here is that you introduce something, some new kind of physics, right? So all of this picture applies if we only take what we know for sure to be out there. So all the particles we've seen, plus the Higgs, plus inflation, and that is the corner you're pushed in. But if there are more particles than that, then you could invent interactions that save the Higgs. And this happens, for example, in the most popular theory that theorists want to talk about, which is the theory of supersymmetry, where you have an additional symmetry of space-time, where you have additional particles in nature, and what these additional particles do is that they interact with the Higgs field in such a way that the shape of the potential never flips over, so it keeps going up. Right? And so that would definitely save your vacuum, because then there's no true vacuum to tunnel into. So supersymmetry, for example, could do it. Even if there's no supersymmetry, you could imagine that the Higgs couples to gravity or to the energy of the inflaton in some way that's not negligible, and that would also save it. You could imagine that quantum gravity can save it. So quantum gravity is this theory of physics that is supposed to kick in at the Planck scale, which is 10 to the 19 GeV. Right? So that is the point at which gravity becomes as strong as quantum mechanics. And all our quantum field theories have to be changed in order to take into account that there's gravitational interactions. And that could give you a whole bunch of corrections. And that could save it, for example. And so there's many ways to save it, and not all is doomed. So just to give you a picture of how that is saved, this is what I would get from coupling the Higgs to the energy of the inflaton, for example. Right? So previously, I had this dark, solid line giving me the potential of the Higgs field. And there, the story was that the Higgs just rolls away to its true minimum, and nothing saves it. If I introduce this coupling, I change the shape of this potential so that it goes from looking something like this to looking something like this. And there, as you can see, there's no such phenomenon, right? So it can only go up, and who knows what happens beyond that. So there are many ways to save it. And in particular, supersymmetry is a very strong reason why people believe that this will eventually be avoided, and then you can sleep in peace. But the fun part of this whole story is that even though there might be things out there that can save you, it's really interesting that the Higgs and the top masses ended up putting you right there, right? So the Higgs mass could have been anything. The top mass could have been anything. And yet nature chose numbers so that we were sitting smack in the middle of this metastable region. We could have been stable, but no, nature had to push us there. And so you can go back into your corners and have these deep philosophical existential questions about why do we live here? Right? So you heard that I was a philosophy major in college. So this is perfectly in line with what I do sometimes. And there's a very close analogy to this line of thinking. And so here's a picture to illustrate it. So it looks like I'm going to tell you a legend from ancient Buddhist philosophy, but this is actually something that came out of physics, and this was has various names. So it goes by the name of the anthropic principle, or the idea of the multiverse, right? And the story there, and this is a story told by Professor Lenny Susskind, who is at Stanford. The story is that imagine that in some corner of our world, there was a tiny pond, and in that pond, there lived a fish who started thinking about physics and philosophy. Right? And so he started growing smarter, and he looked out into the universe, and he saw that there were all these beautiful mountains and forests and cities and valleys beyond valleys where he could have lived. And then he had this deeply existential question: why here? Right? Why not here, or here, or here? Why do I live here? And that line of question apparently is a very fruitful one, because as you try to answer that question, you learn more and more about yourself. Right? So the fish will eventually learn that it cannot survive on land, because as soon as it tries to go onto land, it dies. It cannot survive in a fast-flowing river because of, I don't know what, use your imagination. And so the answer to why here, actually for the fish turns out to be because anywhere else is impossible. Right? So by asking this seemingly empty and deeply philosophical question, it actually learned a lot about itself. It actually learned a lot about the universe or the world it was living in. And so we are confronted with a question similar to this fish, right? So this picture, where we live in a very improbable corner of parameter space, where something really weird happens and not anywhere else, is along the lines of the idea of the multiverse, that our universe is not the only one, right? So there's many, many universes out there, and the collection is called the multiverse, and we just happen to be living in a corner where the top quark mass and the Higgs mass pick up certain values, whereas everywhere else it could have picked up any other value. And so the question we ask is, why do we live in this corner? Right? So why here? Why not live in a universe where the Higgs mass is 115 GeV? Why not live in this universe where the top quark is at 160 GeV? We don't know, but then as we pursue these questions deeper and deeper, we might find out why we cannot live there, and that'll tell us something that is special about our universe. And this is why this question is so fascinating, right? So even though supersymmetry might eventually solve it, all my colleagues, whenever we feel like giving up on this project, and we've been working on this for more than 2 years, so we go back to this picture and say, this has to mean something, right? It's the fact that it's sitting right there and not there and not there. Maybe that's going to tell us something about the universe. And so that forces us to go back and think about these issues deeper. And so I would like to end with this cartoon and not say anything else. Thank you.